In this set of videos, we're going to discuss bias, confounding, and interaction. This slide essentially just highlights some of the main aspects of observational studies that we've discussed in this class. We have the cross-sectional studies, which, as you know, are looking at risk factor and disease at one point in time, and what we're gleaning from that study is a prevalence ratio. Prospective studies, we look at the risk factor and then the onset of the disease, and we typically measure a measure of risk or relative risk. And then finally, in the case control studies design, which is a retrospective design, we're looking among people with and without disease backwards for the presence or absence of a risk factor. And in that study design, we're measuring an odds ratio. In all of our studies, we're always interested in the validity of the results that we gather from those studies. And validity can be put into two categories, internal and external. Internal validity is essentially the idea that the results of the study accurately reflect the true situation in that particular study population. External validity is when we are interested in if the results of our study are applicable to other populations. So you often hear researchers talking about how these data were internally valid, but they may lack external validity because the population who was studied in their study may not be generalizable to the overall intended population or population at risk. Sometimes you hear the reverse. You'll hear, oh, our study has tremendous external validity, the data are generalizable, but there are concerns about internal validity. And that has to do with concerns of a biased measure or systematic error. And that's what we're going to talk about next. But before that, I want to just highlight some different kinds of study variability, which are shown here. And this is not an exhaustive list, but these are some of the main categories. So in a study design, you can have tremendous variability within an individual, right? Imagine you're doing a study where you're collecting data repeatedly over the period of time among people in the study. For instance, repeated measures of blood pressure. There can be variability within the one same individual on that measurement, and that can influence our internal validity. You can also have variability in the measurements that are used insofar as the specific type of testing. Depending on, for example, the particular chosen antibody titer, you may find that you're going to get different results. There's also variability over time in a study, and that has to do with the duration of the study. If it's of a certain length of time, there may be changes insofar as seasonal variations with relationship to the exposure or the disease. We also have variability over time, just in cohort, what's called a cohort effect, where data collected over, say, multiple decades can vary due to different patterns in the populations who are studied or how those populations are changing over time. You can have variability within populations as well as between populations. And this, again, is driven by how the study populations are chosen and then how the sample from that population is derived. So that brings me to sampling variability. And the idea is that the smaller a sample is for the particular study that we're performing or reviewing, the more variability there will be in the calculated measure of association. That hopefully is somewhat obvious to you. Small sample sizes yield large variability. Also, small sample sizes will, because of the amount of variability, will often be insufficiently powered for us to really determine if there's an association. And that's driven by the lack of precision. So in contrast, then larger sample sizes provide more accurate estimates. But importantly, it's good to know or keep in mind that even with large sample sizes, the measure of association may yield a statistically significant result, but that the measure of the effect size may be too small or may be not clinically relevant or clinically important. And so now I want to talk and shift a little bit or look at things more broadly in terms of types of error. And that's where we're beginning now with talking about bias. So you can think of error in two categories. Random error, this is where we just have chance finding or the lack of power, perhaps due to sampling variability or sampling error. And then we can have systematic error, and that's what we're going to talk about next. So systematic error is bias, and it occurs in a study for a variety of reasons, which we will discuss. And when it occurs, it leads to a distortion in the overall study results. It leads to a distorted measure of effect. The bias can threaten our overall study validity, both the internal as well as the external validity, but generally more the internal validity. And bias occurs in all types of epidemiologic studies, including experimental trials or randomized clinical trials. And as I said, it leads to a mistake in the estimate of the effect of the exposure or the risk factor on the occurrence of the disease, and it can affect our measure either away or toward the null. So again, bias is systematic error, and it leads to a lack of internal validity. Now, there are two main categories of bias that I'd like to discuss. The first is a form of selection bias, and the next is information bias. So selection bias has to do with how the data are being collected, have to do with the population who are sampled for the particular study. So it is a distortion resulting from the procedure or methods used to select subjects, as well as factors that influence the study findings. In contrast, information bias has to do with how information are collected among the subjects who are selected for the study. And we'll talk about the different kinds shortly. So first I want to talk about types of selection bias. The first type I want to discuss is called Bergson's bias. This is a specific kind of bias that occurs in hospital-based studies and specific to case control study designs only. And what it does is it leads to a spurious association between diseases or between a characteristic and a disease because of a different probability of admission to a hospital for those with the disease compared to those without the disease, and with the specific characteristic of interest or the risk factor of interest. And I'll give you an example of that in a moment. There's also a bias called self-selection bias, and this is a bias that occurs when individuals self-select to participate in an observational or experimental study that has to do with some particular factor germane to that individual that's different from those who chose not to participate in the study. That's similar to a volunteer bias, but this volunteer bias particularly is associated with people who choose to volunteer in a study because they're worried about their overall risk of the disease, or they're people with the disease and they're worried about what factors they were exposed to that led to the disease. There's also a healthy worker effect. This is a type of bias that leads to inclusion of subjects into an epidemiologic study of people who are healthier and thus less at risk for the outcome than people who aren't enrolled in the study because they're no longer working. So this occurs in studies of workers, and essentially the people who are no longer working because they died or they're unable to work are going to differ in the risk factors than those who are working. And so that creates this healthy worker effect, and it can lead to a bias either toward your null of no relationship or against your null. There's also migration bias, and this is a bias that occurs when you're performing or when you have a long-term cohort study and people are moving in and out of your cohort for a variety of reasons that may or may not be associated with the outcome you're studying, and that can create a bias in your measure of association. And then lastly, the cohort effect bias, which I mentioned a moment ago. This is a bias that occurs in long-term cohort studies where you have a changing in subject characteristics or risk factors or both over a function of time, such as say decades, and then that can lead to a biased measure of association. So now I want to talk about Bergson's bias a little bit more in detail. As I said a moment ago, it's a type of a bias in case control studies that are hospital-based. And the example I'm showing you here is a case control study looking at the relationship between smoking and respiratory disease. So individuals with respiratory disease were the cases, and this study chooses controls as individuals in the hospital who have accidental bone fractures. And again, the question is smoking associated with respiratory disease? So what happens sometimes in this sort of design, where the cases and the controls are from a hospital, you find that there's an overlap in the probability. So in this, it's a Venn diagram to illustrate that. So here you have the probability of a patient will smoke and be admitted to the hospital. Here you have the probability a patient will have a bone fracture and be admitted to the hospital. And then here you have a probability a patient will have respiratory disease and be admitted to the hospital. But what you find is that there is this overlapping in the probabilities among all of these people, such that your measure of association is influenced by the selection of the controls from the hospital where the cases are chosen. So in other words, the potential for the exposure to the smoking may be larger among these controls who were selected for this particular study by the mere fact that they were in the hospital for a bone fracture. They may have other risk factors or other diseases that may or may not be associated with perhaps the possibility of being a smoker. And so this kind of design can lead to a population that really doesn't represent the true control population among people who say weren't hospitalized.